Welcome to Complex Analysis. Today we are going to explore exponential and logarithmic functions. If you have ever wondered how engineers analyze alternating currents or how physicists model quantum mechanics, these are the exact mathematical tools they use. We will build your understanding from the ground up, starting with how complex numbers behave inside an exponent. Let us begin by imagining you are driving a remote control car on a massive flat parking lot. The real numbers act like the gas pedal, telling the car to go forward or backward to cover distance. The imaginary numbers act like the steering wheel, telling the car to spin around in circles. In standard real number math, the exponential function just grows incredibly fast, acting as a pure stretching action. But when we feed a complex number into the exponential function, it presses the gas pedal and turns the steering wheel at the exact same time. It takes a flat grid point and transforms it into an arrow with a specific length and direction. To see how this steering and accelerating works mathematically, we define the complex exponential function. We start by splitting the complex number into its real and imaginary parts. Using the standard rules of exponents, we separate the real exponential from the imaginary one. Euler's formula then converts the imaginary exponential into sine and cosine. In this final equation, the real part x dictates the absolute magnitude or length of the resulting complex number. As x increases, the arrow gets longer. The imaginary part y acts as the angle, measured in radians. As y changes, the arrow rotates around the origin. Before we calculate anything, let us visualize this transformation. On the left, we have the z-plane. The straight vertical blue line represents a constant real part with a changing imaginary part. When we pass this straight line through the exponential function, it perfectly wraps into a continuous circle on the right in the w-plane. The constant real part sets the fixed radius of the circle, while the changing imaginary part drives the rotation around that circle. This geometric transformation is the absolute core of complex exponential mapping. Now that we have seen the geometry, let us evaluate a specific point. We want to find the exact value of the exponential function when our input is 2 plus I times pi divided by 4. Our strategy is to use the expanded formula we just derived. First, we carefully extract the real and imaginary components. The real part is exactly 2 and the imaginary part is pi divided by 4 radians, which corresponds to a 45-degree angle. We substitute these identified values directly into the complex exponential formula, setting up the trigonometric functions that will give us our directional coordinates. Continuing with our calculation, we evaluate the trigonometric functions for pi divided by 4 radians. Both the sine and cosine of this angle are equal to the square root of 2 divided by 2. This tells us that the resulting point lies exactly on the diagonal line, where the real and imaginary coordinates are equal. Finally, we multiply the outside magnitude, e squared, into both terms inside the parentheses. Physically, this means if you start at the origin, you walk this specific distance to the right and the exact same distance upwards. We have successfully transformed our original grid point. Having mastered the exponential function, we now look at its exact reverse operation, the complex logarithm. Think of a clock on the wall with hands that spin around continuously. If I tell you the clock hands have moved exactly 2 hours forward, you know exactly where they are pointing. But if I point to the clock showing 2 o'clock and ask how many total hours the hands have moved since they were installed, you cannot give me just one answer. They might have moved 2 hours or 14 hours or 26 hours. Because the complex exponential function loops back on itself every full circle, the logarithm must have infinitely many valid outputs. To capture these infinitely many answers, we need a new formula. The complex logarithm of a number z asks what complex power we need to raise e to in order to get z. To calculate it, we take the standard natural logarithm of the number's physical length, which gives us the real part. Then we add the angle of the number multiplied by the imaginary unit I. The variable n represents any integer, meaning we can add or subtract full 360-degree spins without changing the physical direction. This addition of the 2n pi term explicitly shows that this is a multi-valued function. Now that we have seen the formula, let us understand exactly where it comes from. We begin by setting up the fundamental definition of a logarithm as an inverse function. We are looking for an unknown complex number w that satisfies the exponential equation e to the power of w equals z. We break both sides of the equation down into their detailed components. We write the unknown power w as a real part u plus an imaginary part v. We also write the known number z in its polar form, where r is its absolute length and theta is its angle. We then split the exponential on the left side into a magnitude piece and a rotation piece. Continuing our derivation, we match the real and imaginary components. The structure of the left side perfectly matches the structure of the right side. By equating the magnitudes, we find that u is simply the standard natural logarithm of the length r. By equating the angles, we find that v is equal to the angle theta. But we must add multiples of a full circle, represented by 2n pi. Finally, we combine our results for u and v back into the single complex number w. This gives the final result, proving exactly why the logarithm produces a vertical stack of different answers. So we have proven that the logarithm gives infinitely many answers. This brings us to a practical solution. To make the logarithm easier to work with, mathematicians created the principal value of the complex logarithm. This is written with a capital L. To find this single unique answer, we strictly limit the angle to be greater than negative pi and less than or equal to positive pi. By forbidding the addition of extra full circles, we force the multi-valued function to behave like a normal single-valued function. This is exactly like telling someone to only read the current time on the clock, rather than guessing how many days the clock has been running. Before we move on, let us see this multi-valued behavior with a concrete example. Let us calculate both the general multi-valued logarithm and the principal value logarithm for a negative real number, -1. In standard real number mathematics, taking the logarithm of a negative number is impossible and causes an error. However, in complex analysis, it is completely possible. Our strategy is to first convert the number -1 into its polar form. Its absolute distance from the center origin is exactly 1 unit. To point at -1 from the positive real axis, we must rotate exactly halfway around the circle, which is an angle of pi radians. Continuing with our -1 example, we substitute our geometric findings into the general multi-valued logarithm formula. The natural logarithm of 1 evaluates to 0, which makes the real part of our answer completely disappear. The imaginary part contains our base angle of pi plus the infinite multiples of full circles represented by 2n pi. We simplify the expression by factoring out the common terms in the imaginary part. This shows that the logarithm of a negative number is purely imaginary. If you plug any integer into n, you will get an imaginary number that perfectly returns -1 when put into an exponential function. Finally, we determine the single principal value for our logarithm. To find the principal value, we set the integer n to exactly 0. This restricts our angle to the standard range between -pi and +pi. The result is simply I multiplied by pi, which is a single unique complex number. This beautiful result proves that the logarithm of -1 is not an error, but rather a specific point on the imaginary axis. We have successfully found both the general and principal solutions. As we wrap up, let us review the most important ideas we have covered. We saw that the complex exponential function takes a flat grid coordinate and transforms it into a stretched and rotated arrow. The complex logarithm does the exact reverse. But because rotations repeat themselves, it provides infinitely many valid answers. By restricting the angle, we can define a principal value to get a single useful answer. Mastering these concepts unlocks the ability to solve complex rotational problems in advanced physics and engineering. You now have a solid foundation in complex exponential and logarithmic functions.